last unit, which is the unit on probability. I mean, hopefully, it'll be more intuitive than the unit on statistics.
Yeah.
Although, I mean, I was looking at your tests as you turned them in. Seems like pretty much everyone did fine. But yeah, so probability is the field that essentially deals with, chance, right? A lot of the time we just think of things as being certain or impossible, and somewhere in between, there's just some vague possibility that we don't really think about, but sometimes it happens, sometimes it doesn't. But probability allows you to put a number to that sort of, those sorts of chances that you get a concrete sense of what is the chance of some particular thing happening, so that you can make better decisions. Not all the decisions we make are certain. So the way that we talk about probability is in terms of outcomes or in terms of events. So an outcome is literally just any result of an experiment that you can do. So this is just an outcome is just any possible result of an experiment. And an experiment in this sense is anything that you can do over and over, and it's the same thing that you're doing every time, but maybe it comes up, with a different result. So for example, rolling a single die is an experiment because you can roll the same die over and over and over, and it comes up a different way each time. Or if you toss a coin, you can toss the same coin over and over, and it can come up one of two ways. It can come up, heads, or it can come up tails. You can extend this to, flipping two coins at once, or rolling three dice. Three dice at once. And, an outcome would just be, what happens when you roll it. Do you get two heads? Do you get a heads and a tails? Do you get a tails and a heads? Do both of them land on their side? I mean, generally speaking, we don't really consider the possibility that a coin would land on its side, but theoretically it's possible. So that's what an outcome is. It's a result of some experiment that you can do. Now, an event is a collection of results that you're interested in because they share some property. So for example, I suppose what it says here is that if you flip two coins, I don't know what a coin looks like. I can't. It's got a person's face on it.
10 out of 10.
Yeah, that's fine. It can come up heads or it can come up tails. I'm sure the Lincoln Memorial is not on the opposite face of like George Washington's face, but so for example, coin one, right? You can have one coin that can come up heads or tails. And you can have a second coin that also comes up, heads or tails. So if you flip both these coins at once, you could get that the first one is heads and that the second one is tails. That is an outcome. You could also get that the first one is tails and the second one is heads. So these are two different outcomes, but they're part of the same event. Because they each have one head and one tail. So an outcome is a particular result, right? But an event is just, it's one or more results or outcomes, right? It's one or more outcomes that you're interested in because they share some property that you're interested in. So likewise, if you rolled 3 dice, and you were interested in whether they came up as 1, 2, and 3, that would be a particular outcome, yes. But if you were talking about the event, getting a 1, getting a 2, and getting a 3, in no particular order, you would also include, that would be an event, and you would include getting a 2, a 1, and a 3, getting a 2, 3, and a 1, getting a 1, a 3, and a 2. Suppose getting a 3, should have just written the numbers on these. And then last, getting a 3, a 2, and a 1. So these are all, these are 6 different outcomes, but they represent the same event. Getting a 1, 2, and a 3 in no particular order. So an event that you're interested in can have multiple outcomes associated with it. It might just have the one, sure, but it can also have more than one. Okay, so let's say that there are families with 2 kids. And let's assume that, let's assume that each of these kids can be one of a boy and a girl with equal probability. The number of outcomes is going to be 4, just because, so the first one can be a boy, and the second one can be a boy as well. Right? So that's one outcome. The first one can be a boy, and the second one can be a girl. It can also happen the other way around. And last, have 2 girls. Now in terms of events, if what you're interested in is the total number of boys in a two-child family, this would be considered one event, because that's, the sort of, that's the quantity of interest, right? The total number of boys in a family. These next two outcomes would be part of the same event, because these both are situations in which there is one boy. And this last possible outcome is an event all by itself, because it's the only situation in which there is 0 boys. So there are 3 events, because 2 of the outcomes are part of the same event. Right, 2B. Okay. So the probability of some of these events happening, right, is expressed as a number. So that's going to be something like probability of, for example, 2 boys, or probability of 1 head and 1 tail in a flip of 2 coins. So it's going to be written like this. Let's see, rolling a 5 on a die. So it's almost like, in a way, it's almost like function notation, just with a p instead of an f. But that's the way that you write the probability of something. P and p with a set of parentheses with the event of interest on the inside, and it's read p of that event, right? P of the probability of 2 boys, p of 2 boys, probability of 1 head, 1 tails. Okay, every probability expressed in this way is in between 0 and 1. Always. That's because a probability of 1 indicates that something is certain to happen. Like, it is literally impossible for it not to happen. It has to happen. That's what a probability of 1 means. So you can sort of imagine why you can't have a probability greater than 1, because how can you be more certain than absolutely certain? And a probability of 0 means that something is impossible. It cannot happen. So, for example, the probability of rolling between a 1 and a 6, well, let's just say 1 and 6, not a 1 and a 6. Rolling between a 1 and 6 on a regular 6-sided die, that has a probability of 1, right? That has to happen. Whatever number comes up, it is definitely going to be between 1 and 6. In contrast, let's say the probability of rolling a $99 on a regular 6-sided die. That probability is 0. It cannot happen. And so most probabilities are going to be like in between 0 and 1. Right? Most of them are, yeah. But for sure, it cannot be less than 0, and it cannot be greater than 1. It has to be between 0 and 1. And so, in a way, you can think of it like a percentage chance that it's going to happen. So, I'm sure you guys know by now that 1 corresponds to 100%, right? And in a way, this is a way of measuring how likely something is to happen. If something has a 0.5 chance, a 0.5 chance, that means it's 50% likely to happen, and 50% likely to not. If something has a 0% chance of happening, of course that means it's impossible. So you can think of these probabilities as also being percentages, if that helps you. The closer a probability is to 1, the more likely it is to happen. The closer a probability is to 0, the less likely it is to happen. So, something with a low probability is not likely to happen. You have a pretty low probability of winning the lottery, for example. You have a pretty high probability of having to pay taxes every year. I mean, not that it's really, up to chance. It's not like the IRS are rolling dice to see whether you pay taxes or not. But just expressed as a chance of it happening. It is a likely event. So probability is going on a scale from 0 to 1. So if you want to calculate a probability, all you do is think of the total number of outcomes that can happen. Right, so if you're rolling a single die, that number is 6. There are 6 outcomes that can happen. If you're picking a card from a deck of cards, there are 52 ways that there are 52 different cards, right, in a deck of cards. If you are flipping a coin, there are 2 ways it can come up. That is that number. And once you have that, think of all of the events that you actually want to happen. That number goes on top. So in a way, you can think of it as the desired outcomes, or the outcomes of interest, right, placed over the number of possible outcomes. So for example, the probability of the probability of getting an even number on a die. Right? Now, if you think about a die, there are 6 ways it can come up. I can have either any one of the numbers 1 through 6. Okay, so there are 6 possible outcomes. So that number goes on the bottom. Now, if you're talking about your outcomes of interest, you're interested in the probability of getting an even number on a die. So that's even, and that is even. So there are 3 outcomes of interest or 3 desired outcomes. Oops. Right, if you are interested in the probability of getting an even number when you roll a die. So that number is 3, that goes on top. And so 3 over 6, that comes out to 1/2. Right, so the probability of getting an even number when you roll a die is 1/2, which is not really a surprise because half the numbers are even and the other half are odd. But that's how you would construct a probability, right? You place the number of possible outcomes on the bottom, and you place the number of desired outcomes on the top. And every time, the probability that results from this is going to be in between 0 and 1. Right? Usually somewhere, in the middle, but it's definitely between 0 and 1. So these things that we're calculating right now are referred to as theoretical probabilities. Right? Because we're not actually, rolling a die or flipping a coin and finding out how many times it, what percentage of times it comes up a certain way. We're just going under the assumption that a coin is fair. We're going under the assumption that a die is fair and that it comes up on each face 1/6 of the time, for example. These are theoretical probabilities. Right? And, we're just creating these probabilities in our minds under some assumptions. Right? They're fair assumptions to make, but they are assumptions. Certain assumptions of fairness. Again, a probability is going to be the desired outcomes placed over the possible outcomes. So the probability of getting exactly 1 head when you toss 2 coins, well, first we have to know the number of possible outcomes that there are. When you roll 2 coins, I guess you could roll them, but when you toss or flip them, there are a number of ways that they can land. They can both be heads, one of them can be tails, and the other can be heads. It can happen the other way around, and it can happen where they land, both tails. So there are 4 possible outcomes. So the 4 possible outcomes goes on the bottom. Now the outcomes of interest are the ones where you have exactly one head come up. So that's this and this. Right? So there are 2 of those that you want to happen. So this number gets placed on top. And so this actually simplifies to 1/2. So the probability of getting 1 head, and implicitly, right, 1 tails also, right? Because if you have exactly 1 head, the other one has to be also a tails. The probability of getting exactly 1 head is 1/2.
I have a question.
Mm-hmm.
So for the desired outcomes, those are the ones that are similar? Is that a way to look at it?
Well, yeah, they should be similar because they should all share a property that you're interested in. The property here is that, they have exactly one of them coming up heads and the other one not.
Okay. So like for head, HH is considered what, just heads?
Yeah, two heads.
Two heads.
Yeah.
So they cannot have two heads. They cannot have both. They cannot be the same, so that it can be considered design. Is that what it is? I just want to make sure that I'm getting it.
Because you want exactly one of them to come up heads.
Oh, okay.
Yeah, not both, not neither, exactly one.
Okay.
Yeah.
Like one to be.
One or the other. Yeah.
Okay.
Now the probability of getting a 3 when you roll a 6-sided die. So the probability of rolling a 3, right? Just rolling a 6-sided die and then 3 is the face that comes up on top. Now on a 6-sided die there are, I'm not going to draw those again. It can come up with one of 6 numbers, 1 through 6. So there are 6 possible outcomes. And there is exactly one outcome of interest, right? You don't want a 1 to come up, you don't want a 2, you don't want a 4, you don't want a 5, and you don't want a 6. You want a 3, and only a 3. So that is one outcome that is desired. And so that probability is 1 over 6. You are interested in 1 out of the 6 outcomes. And in fact, like the probability of rolling any of the 6 numbers is going to be 1/6. Right? Because there are 6 faces that it can come up as, and it's a die is fair, so each one has to have equal probability of 1/6 happening. Yeah. Rolling a 1 is not any more likely than rolling a 2, or rolling a 3, or a 4, or a 5, or a 6. They're all equally likely. Okay. So in calculating a single probability, right, just first find out the number of outcomes that exist, just add all, and after that you count up the ones that you actually want to happen. You place the number that you want to, the number of the events that you want to happen, the number of outcomes you want to happen on top, number of possible outcomes on the bottom. Whatever fraction that comes out is going to be your probability. And each of these also has a decimal representation. 1/2 is the same as the probability of 0.5. 1/6 is the same as the probability of 0.16 repeating. Or like 0.166. Right? It's not one of those decimals that stops. It's one of those decimals that just goes on forever. So both a fraction and a decimal are ways to represent certain probabilities. Some situations, in some situations a fraction makes more sense, and in other ones a decimal makes more sense. But, you can easily get from one to the other. Honestly, even
you
if...
have to turn them into a decimal? Or just in case it appears that way?
Just in case it appears that way, but every time that you get a decimal, you can turn fractions into decimals and decimals into fractions. So for example, if you try to calculate 1/6, right, you just literally do 1 divided by 6, and it gives you the decimal representation. If you end up with the decimal representation, you can, On a graphing calculator, it will be under the math menu, and on a scientific calculator, it'll usually just be some secondary function like that you can see like on the actual face of the calculator. But there's usually something that allows you to turn something into a fraction, or turn something into a decimal. But if you have something, if you have a number, and you want to turn it into a fraction, just select this first one. It's literally right there when you press the math button. Turn the answer into a fraction, right? And express it as a fraction. And that's if you need to go from a decimal to a fraction. So just for those that are unfamiliar, this is the way that a deck of cards is constructed. I mean, I'm sure someone has, I'm sure everyone has some concept of a deck of cards, but if you actually wanted it to be laid out, there are 4 suits in a deck of cards. Each one of these suits is going to have 13 cards for a total of 52. The first 10 are just the numbers 1 through 10, except 1 is usually called an ace, right? So there's an ace of clubs, right? There's an ace of spades, there's an ace of hearts, and an ace of diamonds. So there are actually 4, right, of every number of card. There are 4 aces, there are 4 twos, there are 4 threes, there are 4 fours, all the way up until there are 4 tens. So there's actually 40 of the cards right here. The remaining cards are known as face cards. And they're called face cards because they have people's faces on them. And there are 3 of each of those. Just to make the stack look taller. And they're referred to as a jack, a queen, and a king, right? Sort of in that order. They're not smiling on the actual cards. Okay. So these are known as, well, they're not, these are certainly known as face cards. I guess by extension you could call these number cards, but they're never referred to that way. So for these there are 10 of each suit, and here there are 3 of each suit. Right, so in each suit there are 13, right? 10 of a suit plus 3 of that same suit is 13. So each suit has 13. 13 plus 13 plus 13 plus 13 is 52. And if you want to split it up by what the kind of card is, there are 4 of each kind of card, right? Because there are 4 suits. So there are 4 kings, there are 4 queens, there are 4 jacks, there are 4 of every number. So this is how it's divided up. And additionally, half the cards are black, the other half is red. So this is the nature of a deck of cards. There are 52 total cards. Yeah. If you draw 1 card at random from a standard deck, what is the probability that it is a spade? Well, if we were interested in the probability of you pick 1 card, right? 1 card out of the 52. You're not picking a handful of cards at a time. Probability that pick 1 spade on a single draw of 52 cards. There are 52 cards that you can choose, and 13 of them are spades. Right, so again, it's that, it's the total, it's the possible outcomes on the bottom, right? There are 52 cards that you can draw, and desired outcomes on top, right? You want, any one of the 13 spades will count, right? And there are 13 of them, so 13 over 52, that simplifies to 1 over 4, which, also makes sense because, there are 4 suits, and one of them is a spade, so they're all nice and evenly, distributed. All the suits have the same number of cards, so if you're willing to go with any card that fits one of the 4 suits, your probability is going to be 1/4. And again, because these are so nice and symmetrically distributed, the probability of picking any particular suit is going to be 1/4. So 1/4 would be the probability of picking a heart out of 52 cards, or picking a diamond out of 52 cards, and so on. And this could also be written as 0.25. If you wanted it as a decimal. Okay. Oh, boy. Right. So before we talked about the probability of, what happens when you have, what happens when a family has 2 kids. Now we're thinking about families with 4 children. 2 times, there's going to be 16. Okay. So if we just list the outcomes that are possible, if a family has 4 kids, those are going to be, I'm going to write in capital G's. Let's just write lowercase g's. Okay, so they can all be girls. There's going to be 16 of these, so be sure you want to commit to that if you're writing this down. Okay. You can have one boy. He can be the first kid, the second kid, the third kid, or the last kid. Right? So that's if you have one boy. Now you move on to having the possibility of having two boys. They can be the first two. They can be the first and the third. They can be the first and the last. They can be the second and the third. They can be the second and the last. Or they can be the third and the last. Now you can have three boys. Or, conversely, you can think of it as having one girl. She can either be, the youngest child, the second youngest, the second oldest, or the oldest. And lastly, you can have all boys. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possibilities, right? 16 possible ways to have 4 kids. So the probability of having 2 girls and 2 boys in a family with 4 kids, right? We don't exactly write that, it's just sort of assumed. That should be placed over 16, right? There are that many possible outcomes. And if we highlight the outcomes that have, our desired property, right, that they have 2 girls and 2 boys, well, there's this one, this one, this one, this one, this one, and this last one. Yeah. So that is 1, 2, 3, 4, 5, 6 of the outcomes have our desired property. So. Which this should reduce to 3/8, which is 0.375. Right? An eighth is 0.125. Yeah. So about a 37% chance, right? 37.5% chance. Right? So what this means is that, like, if you just go to a bunch of, like, families with 4 kids, most of them actually will have 2 girls and 2 boys, right? Approximately over a third, about like 37% of them will have 2 boys and 2 girls, but that will be more than any other number of boys and girls. So I guess not really the majority, but plurality. That'll be the most common amount that you'll see. If you just, I don't know. In fact, I don't think I know any families with 4 kids.
I do. 2 boys, 2 girls.
Okay, that's good. It's 1 for 1.
Boy. Like, I have 16 boys and 1 girl in one generation. It's only a boy. My first one was a girl.
And certainly this makes sense as to how like the world population stays roughly proportional, right? Like, I mean, aside from certain cases where a particular, like, why am I talking about that? But like there are countries where they prefer one over the other. They'll do certain things to make that happen. This isn't a sociology class. But in most places, right, there will be a roughly equal amount of males and females, which wouldn't be the case if, like, for example, this was the most common outcome, right? So, I mean, it's no surprise that this turns out to be that an equal number of girls and boys tends to be the most common outcome. In fact, no matter how many kids you consider at a time. Okay, so far these were all theoretical probabilities, right? We were just considering, what are the possible outcomes, in a sort of thought experiment in your head? Which one of those do I actually want to happen? Place one number over the other, you get a theoretical probability. There's another kind of probability known as an empirical probability. Empirical or experimental. And that kind of probability is actually, it's literally measured. It's measured, and it's measured as the number of actual trials or observations that you do. On the bottom. And on the top, you get the number of trials or observations with the desired outcome. So basically, you just count, like, how many times did I try this experiment? How many times did I actually roll the die? How many families did I actually measure? That number goes on the bottom. And the number of ways, or the number of times it came up the way that you wanted, that number goes on top. So it's also called the relative frequency method because you literally take the frequency of how many times the thing you wanted to happen happened, right? And place it over the total number of times you tried. So it's similar to the relative frequencies of the relative frequency table from the last unit. So these are different from theoretical probabilities because you actually go ahead and do an experiment, or you observe a number of things. You actually go out there and do something instead of just sort of thinking about, what are the possible outcomes? What are the theoretical outcomes? In your head. So suppose you're tossing two coins, right, at a time. You toss two coins at the same time. They come up a certain way. You pick them up, start over, see how they come up, pick them up, start over. You do that a bunch of times. In fact, you do that 100 times. There are 100 times that you toss 2 coins at once. So, every time you toss 2 coins, there are a number of things that can happen. If you're interested only in the number of heads, for example, you're only thinking about the number of heads. When you toss 2 coins, it's possible that there are 0 heads, right? Maybe both of them come up tails and there are 0 heads. They can also come up as 1 head and 1 tail, of course, but come up as 1 head. And last, they can both come up heads, and you'll have 2 heads. So let's say that you do this 100 times, right? And of the 100 times, 22 of those 100 times, you get 0 heads. 51 of those 100 times, you get a single head. And 27 of those 100 times, you get both heads. So these are the number of times that they occurred. So we can calculate the relative frequency or the empirical probability of these. We simply take the number of times that an event happened, place it over the number of times that you tried at all. So that's just 22 over 100, or 0.22. For 1 head, it occurred 51 times out of 100, so that's 51 over 100, or 0.51. And for 2 heads, that happened 27 out of the 100 times. So that occurred with empirical probability, right, or experimental probability, 0.27. Now, if we compare these next to the theoretical probabilities, right, you might remember that that when you toss 2 coins, there are a number of ways it can come up. Right? They can come up as both tails, 1 tail and 1 head, 1 head and 1 tail, and both heads. And that's tossing 2 coins at the same time. So there are 4 outcomes. If we group them by number of heads, right, if they both come up tails, that's 0 heads, and that corresponds to 1 of the 4 theoretical outcomes. So that happens with probability 1/4, or 0.25. If we think about the number of ways there are to get 1 head, that's 2 ways out of the 4 ways, so 2 over 4. That corresponds to a probability of 0.5 if we wanted to express them in decimal, which is probably best for comparison in this case. And 2 heads, that happens 1 out of the 4 times, or 1 out of the 4, theoretical outcomes. So that corresponds to, again, 0.25. Now, if we look at these side by side, they're not exactly the same, right? Because in real life, there is an element of uncertainty, right? Like, nothing that you do in real life is going to happen the exact number of times that the theoretical probability says it will. Right? There's some people will, for some people it'll happen less, for some people it'll happen more. It's not like when you, sorry, what's up?
Not an accurate amount, right?
Yeah. Like it's like when you roll a die, the die isn't thinking like, okay, I gotta, make sure that I land on 1, 2, 3, 4, 5, and 6 an exactly equal number equal number of times each time. It's not like the die is thinking like, okay, um, I've hit all the numbers except 6, so I better make the next one a 6 so that it's, completely even. Like it's not thinking that. Um, so the experimental probabilities are hardly ever going to be exactly the theoretical ones, right? But they'll be close to them. And technically speaking, the more times that you do an experiment, the closer that it's going to get to the theoretical probability. But it will never be exact. Like it just won't be exact. I mean, sometimes it might, but there's no rule that says it has to be exact. Anyways, but you want it to be close. So if you compare these probabilities side by side, 0.25 to 0.22, 0.5 to 0.51, 0.25 to 0.27. If you compare these, there's no reason to think that there's no reason to think that they aren't fair coins, right? They're close enough to what a fair coin should do, theoretically, that there's no reason to think that it's a coin that's weighted on one side or something. Those do exist. I mean, you can probably just even shave like a bit of metal off of one side of the coin, make it land on heads more often than tails or something like that. I'm sure that's a thing that's happened. But so empirical probabilities are never going to be exactly the theoretical ones, but they'll be close. Well, they should be close, and they'll be closer the more times that you actually try to do an experiment to get an empirical probability. Right, they are close. There's no reason to think that they're okay. So what we've seen so far are two things: a theoretical probability based on the assumption that all outcomes are equally likely. Right. Okay. So this is simply saying that the probability of an outcome is the number of desired outcomes on top over, I guess I should move this, over the total number of possible outcomes. A relative frequency, which we just saw, so this is theoretical. Okay, so an empirical or experimental probability, or a relative frequency probability, you can also call it that. It's to be measured as the number of times a desired outcome happened placed over the number of trials or observations. Right, but the important part of an empirical or experimental probability is that like an experiment was actually done, like something was measured. They actually had a little sort of chart of outcomes where every time something happened, they put a little what is it called when you do this thing to? Yeah, okay. Like you know, like you can imagine that they had a chart where, you know, every time they put a little tally every time, you know, a particular outcome happened, and they just counted them up at the end and just sort of, you know, announced those numbers. But that's, you know, a relative frequency or an empirical or experimental probability. And last, there's a subjective probability, which, you know, is usually just a figure of speech or a relatively inaccurate kind of estimation. You know, a subjective probability is like, in the past week, you know, 6 out of the 7 days, you know, 6 out of the 7 past days have sucked, so there's a 6 out of 7 chance that today will suck. Or, you know, or I never win money when I go horse racing, so if I go, there's a 0% chance that I'm gonna win any money. Just some sort of intuitive estimate like that. Okay. And so, a statement like, I'm 100% certain that you'll be happy with this car, aside from being probably a complete lie, is going to be subjective. Because it's not actually, you know, it's not measured, it's not like he's saying like, oh, well, you know, 100 out of the last 100 people that I've shown cars to have been happy with the car I've shown them, so, you know, that gives me 100% certainty. He's, you know, that's just something, you know, a person is saying. Whereas a statement like, you know, based on government data, so like, you know, they actually did some observations. Right? The chance of dying in an automobile accident during a 1-year period is about 1 in 8,000. That means they actually looked at, you know, the number of people that there were in a year, the number of automobile accidents that resulted in deaths in a year, or well, I guess the number of people, you know, that died as a result of automobile accidents in a year. They put one over the other, and they reduced it to about 1 in 8,000. That is a relative frequency because, you know, although, you know, it's not an experiment, right? They didn't put a whole bunch of people into automobile accidents on purpose and see, you know, but they did some observations. They observed some real phenomena, and they measured that out to some sort of frequency. So that's a relative frequency or an experimental probability. And last, the statement: the probability of rolling a 7 with a 12-sided die is 1 out of 12, right? Because, you know, a 7 is the number on one of the 12 faces, right? So it's 1 out of 12. And that's a theoretical probability because it's not like they actually rolled a 12-sided die a bunch of times and measured the number of times that it came up 7. They're just saying, oh, in a theoretical sense, assuming a fair 12-sided die, theoretically, that probability is 1 out of 12 because it's 1 out of the 12 faces. So those are all the differences between the different kinds of probabilities that there are. Usually the one that requires the most thinking are the theoretical probabilities, because, you know, with experimental probabilities there is usually just some, you know, data that you have to count up, or just two numbers that you put one over the other. Whereas with theoretical probabilities, you have to actually think about, like, oh, what are the possible outcomes? Which one of those outcomes do I actually want to happen? So theoretical probabilities usually take the most thought. Now, an important thing is the probability of an event not happening. So So the probability of A not happening, in a sense, is the opposite of the probability of A. But since we're talking about probabilities, the opposite is going to be given by 1 minus the probability of A. That's how we get the opposite of something. So, for example, let's say the chance of rain, right? Say that a meteorologist on the television or something says that the probability of rain is, I don't know, 20%. So expressed as a probability, that is 0.20, right, 20%. So if you wanted to talk about the probability of it not raining, that would simply be 1 minus 0.20 or 0.80. It's the opposite of it. It's, the rest of it that makes it add up to 1. Yeah. So you might notice that whenever you add up a probability and the probability of its opposite, that they add up to 1. That's, that's a result of this, 1 minus part right here. Another example would be, let's say the probability of dying in a plane crash is, it is less than driving a car actually. It is safer to fly than to drive. Let's say that's 0.0000, well, actually, no. I mean, I'm just making it up anyways, but it's probably something like this. It's probably less than that. I think how many people fly every single day. Probably more likely to die of a heart attack on the plane than you are of actually crashing. So the probability of not dying in a plane crash should have chosen something that took less words to write. That should be 1 minus the probability of dying in a plane crash, which is 1 minus 0.0001, which turns out to be 0.9999. So the probability of not dying in a plane crash is relatively high, right? The probability of not dying is high because the probability of dying is so low. And of course, this number and this number, they add up to 1. And that's partially due to the fact that you have to either die or not die. You can't half die, It can't half rain, right? It either rains or it doesn't.
Technically, then.
So what's that whole book?
Yeah.
I guess that could be considered half dying.
Yeah.
So
Yeah.
we didn't figure out this theoretical probability anywhere, but it is, the probability of a family of 3 children having 1 girl and 2 boys is 0.375. It's 3/8, or 6/16 or something. That is what it is. What's the probability of a family of 3 children, not having 1 girl and 2 boys? So the probability of a family of 3 children having 1 girl and 2 boys is 0.375. What is the probability of a family of 3 children not having 1 girl and 2 boys? And that's simply going to be 1 minus the probability of having 1 girl and 2 boys, which was given as 0.375, so 1 minus 0.375 gives you 0.625. That's the probability of having literally any other arrangement than 1 girl and 2 boys. And so that happens most of the time. Right? Now, one thing that I really want to make sure that you understand is the opposite of having 1 girl and 2 boys is simply not having 1 girl and 2 boys, right? That includes having all girls, having all boys, having 2 girls and 1 boy. It's not, the opposite is not specifically, 1 boy and 2 girls. Like, it's not, you don't just flip the words around to get the opposite. The opposite is just not having that particular arrangement. So for example, let's say the probability of rolling a 1 on a die, right? That's 1/6, right? It's 1 out of the 6 possible outcomes. Right? So the probability of not rolling a 1 is going to be 1 minus 1/6, or 5/6, right? Because not rolling a 1 means you can roll any of the other 5 faces, right? That those two are opposites. The opposite of rolling a 1 is not rolling a 6, right? Just because 1's a low number and 6 is the highest number doesn't mean that the opposite of rolling a 1 is rolling a 6. The opposite of rolling a 1 is just not rolling a 1, rolling anything other than a 1. So just don't, I don't know, when you're thinking about the opposite of something, just don't immediately go to the other extreme, right? Something not happening, something simply not happening doesn't mean that the complete opposite extreme is happening. It just means that that thing's not happening. We'll continue this on Monday. The homework is there, but